Hey, thank you. Thanks for joining. I know it's been a very hot day at a very cool conference, and we're close to the end of the first day, so thanks for attending. This session is about Apache Kafka and Kafka Streams, which is part of Apache Kafka. My name is Michael Noll. I'm an engineer turned product manager working for Confluent. Confluent is a US-based company founded by the creators of Apache Kafka. We're headquartered in Palo Alto, California. And we're building a stream data platform at the heart of which is Apache Kafka. Since we started about 1.5 years ago, we attracted the great majority of Kafka committers to join our team. And we are working on improving Apache Kafka and introducing Kafka Streams, of course, and also to build the larger Confluent platform. So personally, I am native German, based in Switzerland, not in California. So I'm actually quite happy that I have this opportunity to come to my home country, to Berlin Buzzwords, and speak with all of you about interesting technology. So thanks for having me. Now, before we start, let me also get to know you a little bit. So let me ask the question, who of you has heard of Apache Kafka before? If you have, just raise your hand. Oh, that's, I think, basically everyone. Who of you are using Apache Kafka in production? Whatever the definition of production is. That's 60, 70%. That's pretty cool. OK, so still there are some of you that don't really know yet what Apache Kafka is and what Kafka Streams is. So let me start with an analogy so that we're all on the same page. And since we're in Berlin, where we have so many great cafes, I want to use brewing delicious espresso as an analogy. So imagine you have a data-driven product, and that product would be a very great espresso. What would you need to brew that coffee? So if you're at home, what you would need is two things. You need water, which is a key ingredient for a good coffee, and you need to get the water to your home, the water pipes. So Kafka would be these water pipes. And what's important is that this infrastructure is reliable. There is a continuous stream of water available to you, because if it isn't, you can't brew coffee. And there are further challenges, like you have some problems to go to the restroom. But all of that is not sufficient for brewing your coffee. So you need something that turns the water and some ground coffee into your espresso. So you need a coffee machine for that. And Kafka Streams is the equivalent of a coffee machine in that analogy. Now, once you have all these things in place, you have the water, you have convenient access to the water in a reliable way, there are no water leaks and so on, and you have a very good coffee machine, then you can create a great product and have happy users. Now, before we talk about Kafka Streams, let me take a step back and revisit what the current experience is if you venture into the realm of stream processing. So that is before Kafka Streams, and of course, I'm somewhat exaggerating to drive home my point, but not all that much. So if you decide that my problem is processing data, let me pick a stream processing tool, and then I'm all good. The reality is a bit different. Any one of you has really worked with that in production, this is not a frictionless experience. And figuratively speaking, the question that I want to ask is, how did something that is as simple as this, if you run it on a single machine, turn into something like that if you need more than one machine? So I'll not be talking about Lambda architecture or going through all these things that are good and bad. My point is, there is this tremendous discrepancy between how we would like to work and how we actually do work in practice. So when you're setting out to rethink how you can do stream processing, or when you set out to evaluate existing stream processing tools, you should ask yourself the question, is the tool part of the solution or part of the problem? Or is it actually adding another problem to the ones that you already have? And I think if you want to build a tool that is part of the solution, a good strategy is to make complex things simple and eventually thereby easy and fun. Now, what do we gain if we follow that strategy? One of the gains is developer efficiency. And that sounds a bit like a management buzzword. So let me rephrase that. What we gain is that we scale the human side, like us, our teams, because we don't get better every 18 months. And I think Apache Kafka has done a great job of providing a solution for data messaging, transporting the data, getting it from A to B, and so on. We've heard a couple of talks already today that were making reference to Kafka as a key part of infrastructure. Now, we wanted to do the same thing for stream processing with Kafka Streams. So following the same principle of making complex things simple, easy, and fun. Now, what is Kafka Streams? Kafka Streams is a powerful yet easy-to-use Java library. It's part of open source Kafka, and the source code is available under the Apache Kafka project. Using Kafka Streams, you can build your own applications that are, thanks to Kafka and Kafka Streams, highly scalable, fault-tolerant, stateful, and so on. We talk about that in more detail. Now, before we take a closer look, I want to give you the bigger picture. If you have Kafka in the center of your infrastructure, like your central nervous system for all your data, Kafka Streams is the part that reads data from Kafka, transforms it, and adds value to that data, and writes the result back to Kafka. And then there are other parts of your infrastructure that get the data into Kafka and out of Kafka, such as Kafka Connect, which is also part of the Apache Kafka project. So again, the coffee machine, that is Kafka Streams. Now, while that picture might be good for people that are already familiar with Kafka, some of you might not be that familiar yet. So let me use a Unix analogy. If you have a command pipeline, Kafka would be the pipes, Kafka Streams would be the commands, and Kafka Connect, or the producer and client applications that you can build, would be the parts that get data into and out of the pipeline. The last analogy I want to make is for those people that are more familiar with Java. So when Java was released in its initial version in 1996, machines typically had just a single core. So that's when you had things like java.lang. Some years later, multi-core machines were much more common, at which point things like Java util concurrent were introduced. Now today, you have multi-core machines and you run applications that span multi-machines. But unfortunately, there is no Java distributed. But thanks, we have Kafka Streams that will fill that gap for you. So before we take the actual closer look on Kafka Streams, let me talk a little bit about when you would like to use it. So things that you would like to use it for is when you're building stream processing applications. Today, there are already some reference to fast data applications, so things that create continuous stream of data, do continuous transformation to it, things like reactive and stateful applications, and so on. Things where you might look elsewhere, at least at this point, is everything that is like heavy lifting, data mining, machine learning, and so on. Now, I hear you're like, shut up, just show me some code, right? OK, so in Kafka Streams, you have two options. The first API is a DSL that allows you to express your programming logic in a declarative way. That looks pretty much like Scala, and that would actually be the equivalent of the Scala example that I showed at the very beginning. The second option is a lower-level processor API, which looks a bit more like imperative programming. So you have options to start up your processors. You can tell it how to process every incoming record. You can schedule periodic activities. And you can specify what happens on shutdown. So that's a quick look at the API. But actually, you will not hear me talking a lot about the API. And the reason for that is, I think the API is just a tiny part of what is important when you're picking a tool such as a stream processing tool. There is a whole lot that happens underneath the surface that is very, very important, and arguably much more important than what you see as a developer. For example, operations. So when you look at a tool, or when you set out to design such a tool, you want to do a full stack evaluation of everything that will happen. What is the benefit that you're getting, and at which cost does this benefit come? So in Kafka Streams, just like in Kafka, we wanted to reduce everything that lurks underneath the surface as much as we can. And we're doing this by making complex things simple, easy, and fun. But how do we actually do this at a high level? And the answer is we are outsourcing hard problems to Kafka. They're already solved there. Why should we reinvent that? Now, at this point, I typically see like people like raising their eyebrows. I said, okay, now tell me, how do I install this thing? I said, well, you don't install Kafka Streams, and there should be no installation. It's a Java library, editor application just like any other library. So then people typically have a pause, and they stare at me, give me this suspicious look, and ask me, all right, where is the cluster? And the answer is, I think some of you might already expect the answer, there is no cluster. If you don't need a cluster, why should you? Since when did we have to use a cluster when we set out to do cool things with data? So Kafka Streams allows you to stay lean and lightweight if you want to, and go all out with clustering if you want to. Now the next question then is, okay, how do I package and deploy my applications, or how do I X, Y, Z? And I think the reason why people ask that question is, if you're working on data in your company, you're typically like the guy in the yellow shirt, who is the social oddball, the party pooper, who does things differently than all the rest of the organization. You have a different way to run your applications, to interface with applications, and you actually have a hard time making a case for why people should go for whatever tool you're suggesting. So with Kafka Streams, what we wanted to do is give you the option to do whatever you want to, and we feel it's very important that a stream processing tool should not be opinionated and dictate rules how you package it, how you deploy it, and so on. So that means you can look at this coolness spectrum of, let's say, deployment technologies. You can do either very uncool, boring, old technology that actually work, or you can move all the way to the other extreme of the spectrum and pick the latest craziness on Twitter, whatever is mentioned there, that probably works. So this was more like the look and feel of Kafka Streams. Let's talk a little bit about the underlying concepts of Kafka Streams. And I'll start first with the concepts of Kafka. So since most of you are familiar with it, I'll just be very brief and concise. So in Kafka, you have producers that write data to Kafka and consumers that read that data from Kafka. And the important part is that reading and writing is decoupled. The servers in your Kafka cluster are the brokers who are responsible for serving and storing the data. Now, if we zoom into the Kafka cluster, your data is being organized by you into topics. For example, a topic that captures user activity events. Within a topic, data is being partitioned. Within a partition, data is strongly ordered, and these partitions are distributed across a Kafka cluster for scalability, load balancing, and if you add replication, also for fault tolerance. Now, within a partition, the messages are actually key-value pairs. And I'm only mentioning this because you will see a very strong similarity now that we're switching to the Kafka Streams concepts. In Kafka Streams, you have a stream of data, which is an ordered sequence of key-value records. These data streams are being processed by processor topologies, where the nodes are stream processors and the edges are the streams. If you zoom into that, similar like Kafka has topic partitions, Kafka Streams has stream partitions. And stream tasks are basically copies of the same processing logic that are getting a subset of the data that needs to be processed. So I will not go into detail here, just give you like a higher level view of what that is. The key takeaway is Kafka partitions data for transport, and Kafka Streams partitions data for processing. So there is a close mapping between the two concepts. The reason why I'm very brief here is because I want to talk about something that is more interesting. And that is, there is a close relationship between streams and tables. Now, if you look at the first column, that's like your typical database table. And what you see here is you have like insert and update statements that mutate the table. If you capture all these changes, then you get a stream of changes, a changelog stream. Once you have that, you can reconstruct the table on the left side at another location, which is what you see on the right side. So you can take a table, turn it into a stream, turn it into a table, turn it into a stream, and so on. And we'll see why this is so important. And let me start with an example. So here we have a very simple stream of data, and we look how this stream of data is interpreted differently depending on whether you are a stream or a table. If you are a stream, you look at that data and think, OK, I interpret this as a stream of data records. If you are a table, you interpret the same data as a changelog stream. And the table becomes a continuously updated materialized view of that stream. So at this point in time, both the stream and the table would say, Alice clicked 2 times. If there is a further update for Alice, the stream would say, actually, Alex clicked 5 times. Whereas the table said, no, she didn't click 2, she clicked 3 times. So that example is a bit maybe not so easy to understand, but I wanted to show the same data. Let me use a more practical example where we have different data. The first example is user purchase records that are interpreted as a stream, and the other example is a table with user profile information. At this point in time, the stream would say, Alice bought eggs in the supermarket. The table would say, Alice is currently in Paris. Moving forward in time, the stream would say, Alice bought both eggs and milk, and the table would say, Alice is not anymore in Paris, she's now in Berlin at Buzzwords. So the difference is the stream shows you all the values for a key, and the table gives you just the very latest value of the key. So in terms of the Kafka Streams DSL, there are operations that transform from a table to a stream and from a stream to a table. You can always convert a table to a stream by just iterating through the table. But if you are converting from a stream to a table, you need to provide semantics. If you have a list of input values, you must define, and this is something that only you as a user know, how to squash all these values into one single value as an end result. So a simple example is a join. So let's say you compute user clicks by region, and your input would be Alice clicked 13 times, and the other input would be Alice is currently in Europe. This is how it would look like in the Kafka Streams DSL. And again, I'm not walking through the code. I'm only saying that there's actually this part that we will look at now in an example, and also mentioning there is this region with clicks thing that you may or not be able to read. And the reason we have that is only because Java doesn't support tuples natively. In Scala, it's much more natural. So in this example, we have an input stream, which is a stream. We're joining it with a table to know when Alice clicked 13 times, she was in Europe. And then we are changing the key because we want to aggregate by user region and not by username. And it's still a stream. And now we are aggregating this information to come up with a total count. And in this case, Europe is 13 clicks after the first event, and then it's 18 clicks after the second event. So going back to that picture, there are certain transformations that change the shape of your data structure and certain transformations that don't. And it's important, in our opinion, that your stream processing tool understands that difference and gives you the tools it needs to make proper decisions what is correct for your use case. So lastly, one thing that might not be totally obvious from that example, this table, when you're doing a join, for example, it's continuously being updated with the latest data behind the scenes because it's being backed by a Kafka topic. So as soon as your stream that is joined against that table gets another input, the latest value is automatically retrieved from that table. So that is very cool for building stateful applications. All right, so we talked a little bit about look and feel of Kafka Streams, what it is, when you should use it. We talked a bit about key concepts and so on. Now let me talk a little bit about the key features of the current implementation. First of all, let me take a drink. So of course, by definition, Kafka Streams is 100% compatible with Kafka. So if you have ever had worries that your latest tool doesn't interface well with Kafka, that problem is solved in Kafka Streams. Also, Kafka Streams inherits Kafka's security model. So you can encrypt data in transit, for example, restrict access to certain topics, which is great if you're working on sensitive data like personally identifiable information. In terms of the API, we have, of course, functions that turn a Kafka topic into a stream, a Kafka topic into a table, or a table back to a Kafka topic, or a stream back into a Kafka topic. And when you're writing applications that use the Kafka Streams library, you configure both Kafka Stream-specific settings as well as settings of the underlying Kafka producer and consumer clients. If you're already familiar with Kafka, I think that will be great. If you're not yet familiar, just skip that part. It just means that, yeah, you have a lot of flexibility to fine-tune your application if you need to. When you're using Kafka Streams, you automatically get the following properties for your application: high scalability, fault tolerance, and elasticity. And how does that work? So imagine you have data in a Kafka cluster, and your task is to create an application that processes the data to create something like an espresso. Initially, one machine might be sufficient to process all the data, but at some point you need to scale out. How do you do that in Kafka Streams? Well, you just start literally the same application, the same code on another machine. These two instances will become aware of each other and start dividing the work. If you need more machines, just add more, 3, 4, 10, 20, whatever. If one of the machines goes offline, failure, maintenance, you don't need the capacity any longer, the other machines will become aware of that and start taking over the work. Now, when I started out, when we were designing that, I felt like that is just, I don't believe that. That just can't be true, right? And the reason why that works is, and I'm not going into details here, is because we are outsourcing hard problems to Kafka. Kafka has already concepts like consumer groups and so on that does this rebalancing work between new machines, machines that go offline. So we're just using that. Don't need to implement anything ourselves. In Kafka Streams, you can also do stateful and stateless computations. And an example of that would be aggregations or joins, like the ones that we have in an example. So state stores in Kafka Streams allows your application to manage state. These state stores are isolated, that is per stream task. They are local for best performance, so you don't have to do lookups over the network. And they are replicated to Kafka for allowing two things: elasticity, scale out, shrink down, and fault tolerance. Let's go back to that example. And caveat, this is a very simplified view because of lack of time. So be careful when you jump to conclusions, hey, this doesn't scale well or so on, because it's really a simplified view. So imagine you have your 3 instances of your application, and they do some stateful stuff. So these applications will have, these instances will have state stores, 1 or more. And now remember that we talked about how a table and a key value state store is a table, is also a stream. And that, again, can be converted back into a table. So whenever your state stores change, when they're being mutated, we're sending this information to Kafka and persist it there. So as soon as one of the instances goes offline, the other instances can take care of that work by reconstructing the local state at the point of failure, taking down for maintenance, and so on, and resume the processing. It doesn't need to go always to one machine like in this example, but as I said, it's a simplified view. And how does that work? Again, we're punting the hard problems to Kafka. There's nothing that we need to do in Kafka Streams. Just like back pressure, I will not be talking about back pressure here because there is no need for something like that in the way Kafka and Kafka Streams work. Now, state stores, like how complicated is that? Actually, if you use the Kafka Streams DSL, you won't even be aware of these state stores. They are abstracted away from you. So if you're doing counts, reducing, aggregations, you will not even see them. If you use the low-level processor API, you have direct access to these state stores. So you're very flexible, but have more manual work. But still, it's relatively simple. When your processors start up, you can get a reference to one or more state stores. And then when you're processing records, you can do like gets and puts and so on. So the other thing that is important for a stream processing tool is that it properly models time. And I think the canonical example is the Star Wars franchise. So in Star Wars, we have 7 episodes. And if we look at event time, when things happen in that universe, the first episode was The Phantom Menace, with Jar Jar Binks, unfortunately. Processing time-wise, when they were released and filmed, it's quite different. The first one was in 1977, A New Hope. So if you convert that to Kafka Streams and Kafka, event time would be the time when the producers would generate the original events and send them to Kafka. Processing time would be when your Kafka Streams application actually looks at the data and does something to it. And there's also ingestion time, which is the time when the broker, like the Kafka cluster, received the message for the first time. And in Kafka Streams, you configure the desired time semantics through timestamp extractors, and by default, you get event time semantics. And here you see an example of event time and processing time. It's pretty simple. It's a one-liner how to do that. You can use the same to extract existing timestamps out of your payload if you already have a stream that has that information available. So the other part that is already available in the first version of Kafka Streams is windowing. It's very related to time, so I'm trying to make a link between the two. If you have a continuous stream of data, sometimes you have use cases where you want to break these into discrete chunks. So for example, you want to say something like, I want to get aggregates over a period of 3 seconds, and every 3 seconds I want to get an update of what the latest aggregation result is. And that's what you would call a tumbling time window. So you can easily express that in Kafka Streams. Similarly, there is a generalization of that called hopping windows, where you say, I want to get aggregations for 3-second periods of time, but I want to get updates sooner, like every second, not just every 3 seconds. And then you have multiple of these windows in flight that you won't even notice, but Kafka Streams manage that behind the scenes for you. And why would you need that? There are many use cases. I just show maybe the most obvious one is, if you have a monitoring application like Confluent Control Center, you want to compute and visualize time series of data, and you want to do this across different levels of granularity, for example, 1-minute aggregates, 5-minute aggregates, and so on. So lastly, there are 3 things. It seems like we have 5 minutes left. There are 3 things that I just talked about very briefly. 1, Kafka Streams supports late arriving and out-of-order data. So for example, if you have a 5-minute window, sometimes messages don't arrive within these 5 minutes. Imagine you have an Internet of Things platform, and you're collecting data from devices that are distributed all over the planet. And sometimes these devices have unreliable internet connectivity, so you might get an update from an device, not within 5 minutes, but maybe after an hour, or maybe after a day. So with Kafka Streams, you can define how these late arriving data should be interpreted by your application. You want to discard them, do you want to send an update downstream, and so on. In terms of how fast or what is the latency of Kafka Streams applications, it has millisecond processing latency because it's doing actually 1 message at a time processing, and thus no micro-batching. So if you have a use case that requires low latency, Kafka Streams should be a good fit. And talking about processing, the guarantees that we give for processing in Kafka Streams at the moment is at least once. Because, again, we're building on the shoulders of Kafka, and Kafka does at least once messaging. That said, the work on adding exactly one support is already in the works. That work has already started, and actually one of the engineers who is responsible for that is in this room, but I'm not pointing him out now. So wrapping up. So we did talk briefly about what is Kafka, what's Kafka Streams, when would you use it, and why we think it hopefully advances the state of the art a little bit so that you can build cooler applications with less sweat and tears. Now, assuming that I raised your interest a little bit, you can get it right now. It was released a few days ago alongside Kafka 0.10. And it's also available as part of the Confluent platform where we, as I said, build more than just the core of Apache Kafka in one big platform. We also provide a lot of demos and examples to get you started, like showcasing how to do a canonical word count, how to do joins, how to read and write arrow data, and so on. And if this talk, I couldn't really cover a whole lot of that in detail, but we have extensive documentation that I think is still concise. So we have quick starts, deep dive on concept, architecture, developer guide, and so on if you're interested in that. And lastly, we also do bi-weekly Ask Me Anything sessions. If you're interested in joining these, just drop me a note. Some of the things to come, so what will happen next? I already mentioned we are working on adding exactly one semantics to Kafka and to Kafka Streams. The other thing that we are working on is queryable state. So if you think of these tables that are being continuously updated and kept up to date, oftentimes this is already everything that you need for whatever you're doing, like your espresso. So we want to allow you to directly tap into that state and expose it to you. That will open a whole lot of different use cases that would be a great fit for Kafka Streams, so thereby making your life easier. The other thing that we're working on is a SQL interface, so that you would not need a developer API to express how you want to compute your data. And lastly, but it's not the least, it's the first version that we just released in Kafka 0.10. So we're welcoming all of you to tell us what you like and what you don't like, so we can make it better. So if you have any feedback, I encourage you to share it by letting us know on the Kafka user mailing list. So in regards to things to come, tomorrow morning we have a keynote by Nea Nakede. She's our CTO at Confluent and one of our co-founders, and she'll be talking about the bigger picture of stream processing. So if this talk was a technical view focusing on Kafka Streams, Nea will talk tomorrow about the bigger picture, the strategic view of what stream processing is, where it fits in, and so on. So I think we still have time for some questions now, but if you're not feeling comfortable to ask your question in front of everyone, you can just find me after the conference. Thank you.
So I have a question about the state store, and I think it's pretty clever, pretty smart to push the data back into Kafka. But wouldn't that mean, like, if one node goes down, that it can take quite a while to recreate the state in another node?
So shall I repeat the question for the recording, or is that fine? It's fine. Okay. So one thing that we're exploiting here is a feature called log compaction in Apache Kafka. And I hope I find a very quick way to summarize that. If you're having a stream of data, let's say, with a lot of updates for Alice, as in one of the examples that we showed, what log compaction will do is, it will say, I have 10 updates for Alice, but since state stores are interpreted as a change log stream, I can throw away all the updates but the very latest one for Alice. So if you have 1 million updates for Alice, what will end up in Kafka after log compaction is just a single entry. So that is why it will be very efficient. Does it answer your question? Okay. Okay.
What if after compaction I still have 1 million entries? They would have to be recreated on another node, right? And it will just take time. So even though it might be like normally like millisecond latency, there might be 1 minute pause or something in processing, right?
There will not be a pause, but it will take a while until the data is being restored to exactly the state when the failure happened, yeah. So we pay some cost in the presence of failures.
Hello. There's quite a few things that I think originally might have been in Samza, or Samza was kind of on the way to getting towards doing. Was there any reason that, is Kafka Streams like a new rewrite, or does it include Samza, or is Samza going to sort of fade away now? I'm not really sure. What do you think?
So I will not be able to speak for the Samza project, but of course there are some strong similarities between Samza and Kafka Streams, to the point that some people, not us, are saying like it's like Samza ++ or so. I think that is not a fair comparison. But some of the people that work on Samza are now in our team. So what we actually did with Kafka Streams was we looked at all the prior art in that space, academia, open source tools like Samza, and we said, okay, what are the things that we can cherry pick here? And what are the things that we consciously decide not to do to keep Kafka Streams simple? Which is like a pretty abstract answer to your question, but I think that's the higher level answer. A concrete example would be that in Samza, there are two things. One is it typically wants you to run in Yarn, and we felt like, oh, that is a pretty huge investment. I mean, if you have ever worked in a larger enterprise, telling the governance board, your manager, whatever, just because you have a stream processing problem, to install Yarn, that will not fly. So we didn't want to make the same mistake. Or basically, we didn't want to make you run into the same problems. The second part is, the second example is that in Samza, Kafka is used as the default messaging layer, but it is pluggable. What that means is it's like the smallest common denominator for messaging. And in Kafka Streams, we said, no, we're not going to do that. No one ever swapped out Kafka for Samza. So we're actually embracing Kafka. And by doing so, yes, we're telling you that normally you will always read from Kafka and write back to Kafka. But we can punt a lot of hard problems to Kafka and by really embracing it. So if you ever used, and I hope this is not a long-winded answer to your question, if you ever used one of the other stream processing tools, they often implement their own messaging layer. So what does that mean? So let's think about it in terms of like economies of scale. What you want to do is you want to build a stream processing tool that is very good at stream processing. And then you feel like, oh, wait a minute, I also need to pass messages around so we can do the processing in a distributed system. Let's also solve that problem. But actually, we learned in Kafka, solving the messaging problem is really tough all by itself. So why would you want to re-implement this as like a second or third or fourth priority if what we want to do is stream processing? So and with Kafka Streams, what we can do is, whenever there is an improvement to Kafka, hey, we added security. Guess what? You get it for free in Kafka Streams. You have better performance in Kafka, you get it for free in Kafka Streams. So for us, it's also economies of scale when you're maintaining the project by making it simpler and benefiting from all these other projects when they're doing innovative stuff. And I think a sample that I was alluding to is deployment frameworks, resource managers. Whatever you're doing in your stream processing project, you will never be as good as resource manager as like Mesos. And why is that the case? Because their purpose is to solve this exact problem. You will never get better with like something that you do at this, on the side. So I think some of the lessons learned and the similarities between Samza and Kafka Streams is that we looked at what worked and what didn't and tried to improve upon that. But in terms of like actual taking over code, that didn't happen.
Very good.
Thank you.
Anyone?
I have a hard time seeing most of you.
Thanks a lot.
OK, thank you very much.